What is the graphical language in finite dimensional vector space?
Thank you. So hi, I'm Boldy, and I am going to be talking about completeness of graphical language in this paper. But first, I'm going to have a gentle introduction to the ZX calculus, and then I am going to maybe go into a bit deeper waters and talk about what we actually did. So first, a very, very gentle introduction to ZX calculus. So first of all, ZX calculus, we have spiders in the ZX calculus. We have the Z and the X spider, therefore ZX calculus, or green and red spiders. And they correspond to these matrices. And it's a bit hard to understand from just looking at these bracket notated matrices what they actually mean. So I kind of want to go into detail how to think about these spiders. So first of all, I think some of you are probably very familiar with quantum computing, but most of you will definitely know classical computing. So there you have bits, right? So you have 0 and 1. And that's the same for quantum computing, but there you have these cat 0 and cat 1. So they look the same, they kind of do the same thing, but quantum computing does more than just having bits. You also have the superposition of states. So one of the most basic example of a superposition would be the Hadamard basis. So here, the green spiders with one leg represent the Hadamard basis cat plus and cat minus. And what would happen if you would measure this, in half the time you measure, you get cat 0, and the other half time you get cat 1. And then the last element you might find in the ZX calculus is the Hadamard box. So what the Hadamard box does is it simply relates the computational basis states and the Hadamard basis. So it maps cat 0 to plus, and cat 1 will be mapped to cat minus. So with this, we are able to compute the underlying matrices, what these boxes represent. So for example, in here, we know that this represents cat 0, and this is cat plus. So we know that this is cat plus and bra 0, and the same with cat 1 and cat minus. So we know that the Hadamard box will represent this linear map, and then we can look at the underlying matrices, sum them up, and we indeed see that we get the Hadamard matrix. Then we have spiders with multiple inputs or outputs, but the most basic example would be the Z spider with 2 legs out. So what it does is simply copies computational basis states, right? So if you input cat 0, you get 2 of them. If you input cat 1, you get 2 of them. And we can just very simply write it concisely as a single diagram. And we have the same for, we can have the same kind of description for the X spider. So if you have 2 inputs, you are going to get the summation of the input states. So here we have cat J and cat K. And if you put them into this X spider, then you get the summation of the 2 modulo 2. So it's the XOR. So after this, we can also compose these diagrams. This is very familiar to you. So we can compose them in parallel, and then we can compose them sequentially to build up bigger and bigger diagrams. All right. And then this diagram is actually what corresponds to the C-NOT gate. And if someone is not familiar with what the C-NOT gate is, it's called the control NOT. And with our knowledge, we are already able to see why this is called the C-NOT gate. So first of all, we see that we have some computational basis J in a Z spider that copies it through. So we have 2 J's, and then the X spider will add the 2 basis states up. And so at the top wire, what we see is that we got the identity, so nothing happened. And at the bottom, we got the 2 basis states summed up. So if J is 0, this is going to be also the identity. If J is 1, this is going to be the NOT gate. So the top qubit control the second qubit. So it's going to apply a NOT gate if the top is 1. Okay. Last thing we have in the ZX calculus are phases. So these phases correspond to this e to the I alpha phases at the cat 1 bra 1. And what they allow us to do, or another way to look at them, they are rotation matrices around the Z and X axis. And what they allow us to do is we can express certain quantum gates with these phases. For example, the simple NOT gate is just an X spider with a pi phase, or the S and T gate, which some people might be familiar with, are the pi/2 and pi/4 gates of the green spider. Sorry, this is not the original color, but these are the green spiders, these are the red spiders. So we can represent many quantum gates, and in fact, we can represent any kind of quantum gate. Any kind of linear map between qubits can be expressed in terms of ZX diagram. And this property is called universality. So in other words, the interpretation functor is full. We can get to any linear map between qubits. So other than representing diagrams and quantum processes, we can also reason about these. And therefore, we have a set of rewrite rules. And we actually have seen quite a lot of them. So this is the copy rule. We have seen this is how we have described the action of the Z spider. So this is called the copy rule. We also have the fusion. The fusion is something else we have seen an example of. So if you can remember, we had the X spider with 2 inputs, the red spider with 2 inputs, they summed up. And that was an instance of an X spider fusion. But we could have the very same thing with the Z spiders. And then we have the color rule, so the color change rule, which means that if you have a spider surrounded with Hadamard boxes, it changes its color. And this is again something we have seen an instance of. If you had the cat 0, then it changed its color to the green in the beginning of the presentation. And the last rule I'm going to mention is this only connectivity method, which means that you can drag spiders around as you wish. So it doesn't matter how spiders are connected. The only thing that matters is the inputs and outputs. As long as these are at the same place, you have the very same linear map. Or we can have something a bit more interesting. As long as inputs and outputs are at the same place and their connection and the connections of the spider are the same, you get the same thing. So getting together all the axioms in a slide, this is what we get. So here we have some of the rules we have already talked about. We also have Z and X elimination for the identity. We have bioalgebra, the way to decompose the Hadamard box in terms of Z and X spiders. And we have this permutation rule describing how we can go from rotation around ZXZ to XZX. Okay. And it turns out that these rules are rich enough to derive any equation that holds for linear maps between qubits. So effectively, ZX calculus have the very same reasoning power as matrices you would use to reason about quantum computing. Okay. Just a very quick example, the quantum teleportation protocol. This is how you describe what you should be doing to perform quantum computation. And this is it in terms of ZX diagrams and a way to write it. So you have a shared entangled state. And then Alice prepares some kind of state, applies a CNOT gate, a Hadamard gate, and then measures. She sends her measurement outcomes to Bob, and then Bob corrects these using the measurement outcome Alice has sent. And then what you do is just apply simple rules of the ZX calculus. So first fusion and color change, then again a fusion. And then what you see here is that you have 2b pi, and this is going to correspond to 0 because you have a 2 pi times something, which is 0. So you can eliminate it and fuse together the 2 Z spiders. Again, can be eliminated. And here you have just a single wire that you can drag to Bob. So what you have done is you have teleported your state from Alice to Bob. Okay. Any questions at this point? So this has been the introduction to ZX calculus. If someone has any questions, then I'm happy to answer now. If not, I am going to continue. So the ZX calculus is a really good tool, and it has many applications, some being, for example, quantum circuit optimization. It's a very obvious example, or measurement-based quantum computing, or I could list a lot more. But what we can do is we can introduce a new generator called the W node, the W node being this black triangle. And here I'm describing what it does. So it maps cat 0 into two cat zeros, and it maps cat 1 into the superposition of 1, 0 and 0, 1, 0, 1. Right? So it's a new generator. And it turns out that the Z and the W are already enough to have a universal and complete calculus, but it has different kind of applications. So we have seen ZX calculus was good for MBQC, measurement-based quantum computing, and circuit-based models. The ZW calculus is better if you want to talk about kind of summing up certain kind of diagrams or linear optical quantum computing, multipartite entanglement. And it turns out that if you put together all these generators, you get the ZXW calculus, and this has more uses than just ZX or ZW. Namely, we can express summation and exponentiation of Hamiltonians like this, or we can differentiate and integrate ZX or ZXW diagrams. And now I'm going to start talking about the paper we have been working on. So the completeness of the Q-finite ZXW calculus. So with this, we have a graphical language for finite dimensional quantum theory. So first of all, finite dimensional quantum theory. I'm going to call F here the category of finite dimensional Hilbert spaces. And what we have talked about so far was F here 2, so qubits. F here D would be the subcategory of F here, where Hilbert spaces have dimension of d to the power of n. So here we had 2 to the power of n. Now we could go into qubits, where we have a d to the power of n. So qubits have states where they are in the superposition of cat 0 and cat 1. But what we can do is go further and have, for example, a cat 2. So cat 0, cat 1, cat 2, that would be a qubit. Or we could go further and have any kind of qubit which has d computational basis states. And so here I'm going to just briefly show you motivation or significance of the result we have. So the history of completeness results over the years. So first of all, Miriam was the first to show completeness for the ZX calculus. That was back in 2014, and that was the Clifford fragment of the ZX calculus. And later, Amar showed the completeness of the universal fragment of the ZW calculus, and based on that result, the Clifford plus T fragment of the ZX calculus was shown to be complete, and then later the universal fragment of the ZX calculus was shown to be complete. In the meantime, so this is all qubits, F here 2, right? Another result we have had was from Harney, the co-author of the paper, who showed the completeness of the Q-trit Clifford ZX calculus. And recently we have had a result from Robert and Tituan showing that all odd prime dimensional ZX calculi are complete for the Clifford fragments. So what we had last year was a complete calculus that was complete for all D, so all qubits. It was complete, and what this work does, it goes one step further. So these were all qubits, right? So Hilbert spaces of dimension d to the power of n. But this is any kind of Hilbert space. So we go away from just qubit quantum computing, we go into quantum theory, finite dimensional quantum theory. So this is a much richer place to talk about. So the Q-finite ZXW calculus. So first, I'm going to briefly describe the qubit ZXW calculus. it's very similar to the qubit that we have seen. And then I'm going to go into detail with mixing these dimensions. So first of all, we have standard basis, so computational basis state. Kj means ket d minus j. The Z spider still does the same as it did with qubits, so it copies computational basis states. And the X spider sums computational basis states and takes them modulo d. So they have the same kind of intuition behind them as they would have in qubits. We also have the multiplier. The multiplier multiplies computational basis states with the weight of the multiplier, so m in this case. And then we have the W node. It's again generalization to qubits. So here ket 0 goes to ket 0, 0, and ket j or ket I would go into the superposition of j0 and 0j. And then briefly, so we have had the Z spider in the qubit ZX calculus, and it was a rotation matrix, right? So this corresponds to e to the I alpha, where alpha was our parameter. What the Z box allows us to do is have any kind of complex number here, not just those that are of this form. And then generalizing it to qubits, you need to have not just one parameter, but d minus 1 parameters to describe what Z boxes do. And then our generator is the one that has arbitrary number of inputs and outputs. Okay, so going to mixed dimensions. So what we have had so far is only qubit elements. So these never interacted with other dimensions. So for example, you could have a qubit and a qubit, but you would never be able to connect these two things. This is not allowed. But what you could do is just connect the qubit parts together, those that have the very same dimension. And what we want to do is make these wires interact somehow. So we have this dimension splitter. This dimension splitter acts as the identity. It makes two smaller dimensions into one bigger, which is the product of the two. And then you are able to do higher dimensional reasoning. So here, for example, you would be able to connect the D and the qubit and make a 2D dimensional wire. And we have this notation, which we can define in the language. It's a mixed dimensional Z box. So what it does, it behaves the same way as the Z box in the qubit case, but you cut off at the minimal dimensions. So what do I mean by this cutoff? Just as an example, the mixed dimensional copy rule. So here, if you have some ket J and you want to copy it through to other kind of dimensions, then you will get the copy if the computational basis states you copy is smaller than the output dimensions, because otherwise it doesn't make sense. So otherwise it's the scalar 0. And this can be expressed as the following diagram concisely. We have mixed dimensional fusion, which generalizes the qubit fusion to mixed dimensions. We have mixed dimensional trialgebra rule. And we also have a rule to relate the dimension splitter to Z and X spiders. And lastly, what we have is a normal form. So this normal form, so if you have any kind of vector you want to represent in the language, then it always has a normal form. So here, A0, AI, AM-1, all in these Z boxes, and then connected in a certain way to the outputs. And the interpretation of that diagram will always be exactly this vector. So one of the consequences of this normal form is that the interpretation functor is full, right? Our language is universal. And now I'm just going to briefly explain the idea behind the completeness rule. So first of all, we only need to care about states, because if you have two linear maps, then you could just bend the wires and then reason about the two states. And then if you have the normal form, if you have a normal form and you have two diagrams that you know they have the same interpretation, then you know that going from the if you can rewrite the diagram into its normal form and the other one too, then you know how to write D1 into D2, because you can go from D1 to N and then just apply these rewrite rules in the reverse order. Then just a quick note. So any diagram has this form. So we have layers of diagrams, these A's, and these A's will always be the composition of generators. So this is how states will look like. And then what we want to do is rewrite this whole diagram into a normal form. So what we do is first rewrite the top part into its normal form. So what we have to do is rewrite each generator into its corresponding normal form. Then we just simply bend that diagram and rewrite again the top layer into its normal form. Next step is rewriting the tensor product of two normal forms into a single normal form. And lastly, rewrite a partial trace normal form into its normal form. So if you have these things, then you can keep applying these steps, and in the end, you will consume your diagram. So we'll end up with a single normal form. So just to sum it up, we have to show that generators can be turned into their normal form, tensor products of two normal form can be turned into normal form, and the partial trace normal form can be turned into a single normal form. So this is what we do in the paper. So I'm just going to go through them. So the Z box, for example, can be turned, the W node, the Hadamard box, and the dimension splitter. And then the tensor products and the partial trace normal form can be turned into a single normal form. So with all of these, we have the completeness of this language. And what does this mean? So it means that we have now a language which is monoidally equivalent to the category of finite dimensional Hilbert spaces. So why is that? Two categories are monoidally equivalent if there is a monoidal functor between them, and this functor is full, faithful, and essentially surjective on objects. So first of all, the interpretation functor is the monoidal functor. Then fullness and faithfulness are the consequences of the existence of the normal form, so the universality. And the theorem 3 was completeness. So we have a complete and universal language. And lastly, it is essentially surjective because for any Hilbert space H, we have an object in ZXW. So this is the singleton list containing the dimension of H, such that there is an isomorphism between H and C to the power of the image, which is the interpretation of the object. So the category of ZXW is equivalent, monoidally equivalent to the category of finite dimensional Hilbert spaces. And then, so now we have a great calculus, which is equivalent to finite dimensional Hilbert spaces. What can we do with it? For example, we can reason about spin networks. So for example, this is how you can represent the symmetrizer of a spin n over 2, where you have some interesting factor in the middle. And this is an upcoming paper we are working on. You can also represent light and matter Hamiltonians using this calculus. Or quite interestingly, you can try to come up with a programming language for quantum computing. One very example very nice example would be the quantum Fourier transform. So this corresponds to quantum Fourier transformation, and you can represent it in our calculus using just this very simple diagram. So you apply Hadamard gate in this very high dimensional wire that you obtain by applying dimension splitters and mergers. And lastly, one thing we have been working on is showing that you can get a complete calculus for finite dimensional Hilbert spaces only by having Z and X, such that Z is also mixed dimensional. So it's the mixed dimensional Z spider. If you have these things, you also have a complete calculus for finite dimension. And with this, I thank your attention.
Can you go back to the history picture where?
Yeah. Yes.
Yeah, so if I understand correctly, on the y-axis, you have like the language contains more and more stuff, right?
Yeah.
So the question is, now you proved that the universal version of ZXW is counted complete for mixed dimensional, finite dimensional universe.
Yeah.
Now the question is, can you bring it down?
Well, that's a very good question. So we haven't looked into this, but I think it's not an obviously easy problem. For example, the universal completeness wouldn't imply the completeness of the Clifford plus T fragment. So this is very much not easy. I'm not sure if there is a method to do that, but you can, yeah, definitely try. It's an interesting.
Incredibly hard.
Yeah.
The question is because I guess that if you could bring like the kind of problem I see from a computational point of view is that if you allow for any complex number into your diagrams, obviously for like computational simplifications and stuff, then I have always like a continuum of stuff to pick from, which could be too much. Well, for instance, the nice thing about using Clifford is that you have a limited selection.
Exactly.
Now, my feeling is probably you'll still need a lot of things, because if you have a continuum of things to express, you cannot for certain be finite, I would guess.
Yeah.
But it would be interesting if that could be brought down in a way that's computationally helpful. For graphical has but for Hilbert, yeah.
It is actually a very complicated problem for the Clifford fragment, because we don't even have a universal language just for the qubit Clifford fragment. We don't even know if everything can be represented there using just ZX. Yes.
So you've proven that this is equal to and finite dimensional space is equivalent to but oftentimes, like, in cases of interest, and if the physical system has some sort of structure that is not necessarily like integers modulo d. In their case, like for example, if the square sum of your functions on some finite group or some finite ability, or simply also we have thought about how we could do a bit less evil and have like spirals that incorporate the structure. Some spaces to grow some of the functions like on a larger class of groups, and then just use the finite cyclic groups.
Yeah.
That would be very useful.
We haven't thought about it. We did think about trying to not use the Hadamard gates, but instead the X spider, but it did turn out to be a bit more cumbersome. Maybe you're gonna have
I think we should do it before. So if we don't use the and then we do that, then maybe we will generalize to any community center and all together.
Would be interested if you come up with any useful laws about these dimension mixers. So if you look at its normal, form, it's a big mess, right? So I
Yeah.
know it's just a cute full normal form of thing, but actually, so for instance, this verification task of turning just to add more data into the whole QFT circuit, you really want some laws with the dimension users.
Yeah.
Work, right?
Yeah, so I feel like what the rule that actually makes the most useful rule, in my opinion, but it might be disputed, is the rule that relates it to the Z and X spiders, so this one. A lot of times, so what we started with is having a Q finite ZXW calculus, and later on we realized that the mixed dimensional Z spider is quite useful to reason about things. And then we realized that this relation holds. And using this, you can often relate stuff that happens here into the higher dimensional case. So one example would be if you input certain basis states here, then they copy up and you see how you get the multiplication and then they add up. So this is one of the useful rules. I think.
Flag there, that's the, I think that means multiplication.
This is
Yeah, I lost track of that.
this is so what it does is it multiplies your basis state with n. Yeah. So this is useful to derive rules, definitely. And also it's actually quite nice to reason about the quantum Fourier transform. We do have an idea how to show the equivalence of that circuit and the diagram I showed. So what you can do is, there is a Hadamard gate, you pull it out, you do interactions here, and in the end you can do a bialgebra here. And then that in the end might end up with the circuit you actually have, but we haven't gone through the whole thing.
Good. So the most basic Completeness proof that I know of, the most basic Completeness result I know of is the category finite sets with digital union. It's like the one category generated by a symmetric usable, right? That's the babyest example of this type of result. The category finite sets and Cartesian products, as far as I go, representation. And I kind of feel like now you can do differential quantum theory. A very hard problem like multiplication of finite numbers might be the picture. The deterministic. Yeah, so these are basically like 0-1 matrices.
So by the way, also this means this language from the finite dimension, it also means this is a reconstruction of quantum theory.
Okay, we close this session. We thank all the speakers again.